Hello, my name is Grant Mackenzie. I'm a teacher at Porthcawl Comprehensive School and I'm working with Callum Cymru today. We're going to look at the AS Maths Statistics course, one of the topics being the data presentation and interpretation. Now we're looking at these in terms of revision. So I've taken out specific questions and I'm going to be sort of looking at those questions, and I'm also going to look around the wider elements of them as well. So when we go through each of these, it might be an idea to pause them, but I do suggest that you then look through the whole video, as I will be adding questions on so that you get a full understanding of what is expected from the exam and also expected the skills expected from you as well. So if we start off with the first element. So here you're expected to be familiar with box and whisker, cumulative frequency, and also histograms. So I've taken histograms specifically on this first page, and then I very much doubt they'll ask you to sort of draw one. It's either going to be fill in the missing elements, or it is going to spot different things that they may have sort of omitted, or things from a histogram that you're going to then have to write to. For example, if they've gone up on the frequency on the y-axis, it should be frequency density. If you have a look here, this is a partially completed table and histogram, and it's given information of ages of passengers on an airline. Now, it doesn't matter what the context of the question is, but what I would suggest to you always, as a conclusion, whenever you're writing these things, is to always relate it back to the question. Okay, so whatever the context be in, make sure if you need to write a conclusion, it is always in the context of the question. If you can see here, we have the frequency density. We have also the formula for which is going to be frequency density. So it is FD is equal to the frequency divided by the class width. My writing is actually bigger than expected for this, so I'll tone it down. It's just getting used to writing with this PowerPoint. So if you can see, we have information on the table itself that between 5 and 20, we know that the frequency is 45. So if we were then to calculate what the frequency density would be, it would be the frequency of 45 divided by the class width, which is 15. So I know that the frequency density is 3. Now, as you can see, each one of these would go up in 3. So now we know the scale on the left-hand side. Working out the different frequencies for the frequency densities for each of the following is going to make that slightly more straightforward. So if I was to write them in here, this one is 5 over 5, which is going to give you 1. So then you would expect to draw that element in there. The next one, we need to work out the frequency. So if we rearrange this, then our frequency is going to be equal to the frequency density multiplied by the class width. That's just changed the subject, and as A-level students or AS level students, I expect that to be something which is straightforward. So when we have, it's very difficult to sort of read, but this is going to be 5.2. So that 5.2 at the top here is going to be multiplied by the class width, which in this case is equal to 25. That will give me a value of 130. So if I put 130 in there, and then for the last one here, it is going to be a height of 4. So that is 4. And then that is going to be multiplied by 15, which would give me a value of 60. It is going to be 60. And then obviously we need to complete the frequency density for the last bar, which would be 90 divided by, and then obviously the class width is 20, and that is going to give you a height of 4.5. So then again, 4.5, it's difficult to sort of read where it is, but it's approximately there. So we complete the histogram for the 3 marks. Now, what type of questions would they be asking you? Well, the area which I've sort of put in there, and the frequency density height. They could also ask you to work out what the median or estimated median is from this information given. Now, this is a GCSE topic, which, if you remember, if we were to add up all of the frequencies, it would give us a total frequency. So if we were to sort of say part B, work out the median, we would need to find the location of that median. So if we were to add up all the frequencies, we would have a total frequency of 336. So then the location of the median is 336 divided by 2, which would be 168. If you remember, you need to identify where the median is going to be, or which bar it is. So if we add the 90, the 45, and the 5, we would get 140. And then we would need to find 28 onto that. So we know that it's in this bar here. So 28 onto it. So the value of the median is going to be 40, which is the lower point, plus, or the lower sort of bar value. And then it's going to be 28 divided by, and then what's in there is 130, and times 25. If we then work that out, you should get a value of 45.38 or 45.4 to 3 sig figures. Those are the types of questions that I would expect you to have in a histogram question. On the next sort of slide, I'd like to talk to you about the skew of the slide. Hang on a second. On the next slide, we'll be looking at the skew of where the histogram is drawn. So if it has a positive skew, then it will be going into the and just convert. And that is frozen for some reason. Okay, and as you can see, I've given a couple of examples of what a sort of a positive and negative skew would be. The first one is a negative skew because you have the tail into the negative region if you would draw it like so. On a box and whisker plot, a negative skew has tail in the sort of negative region, and it would look something along those lines. The interpretation of this being negative is you have fewer smaller values. So the majority of cases is the top end. So if this was heights of students, I'm just taking it from a graph where the majority of students are the top end. So they're between 26, 27, 28, 29 centimeters tall, and you have fewer students at the bottom end of 114, 115, 116. For the next one, again, it's just heights of students again, and then you can see here that the tail goes into the positive region, and again, the box and whisker plot would look with the tail going in. So if I write in negative skew, the top one, and then positive skew. And as I said, with the positive skew here, you would have fewer sort of larger values in this case. Okay, and then a normal or a symmetrical skew would be that you would have sort of almost like a bell shaped, where it would look up and down, so it is symmetrical. And then if you just fill in the histogram values like so, and then you can see it would look something along those lines, and that would be a symmetrical, where the mean, median, and mode would be the same value, whereas they would be slightly different in the negative and the positive skew. So here what I've done is I've taken two sort of data sets. Reason being is they're not going to ask you to draw a cumulative frequency diagram or a histogram, but they may ask you to sort of state what the widths are, or the frequency density is, or what are the sort of the first three coordinates on a cumulative frequency diagram. Now, the first one is a bit unusual because it says correct to the nearest centimeter. So the table gives grouped in frequency distribution of arm lengths of 100 women, each measured correct to the nearest centimeter. Now, because they put it correct to the nearest centimeter, they've changed it from continuous data to discrete data. So you have to be careful when plotting this. Notice with the one underneath, it's got the inequalities in there, so it's going to be continuous data. And normally, we would say if it wasn't sort of correct to the nearest centimeter, the above information would be continuous as well. Whereas continuous is flowing, discrete normally goes up in sort of steps. And because they put the nearest centimeter, they're making it in steps. So we would need, a question could quite honestly ask, write down the first 3 coordinates of a cumulative frequency diagram. Now, in doing so, if I was to change color here, this sort of value is 156 to 158. Now, with a cumulative frequency diagram, it has to be that continuous motion between them. So we're going to have, on the bottom here, 155.5, and in the middle here, 158.5, because we're going to have that step up. Okay, and that's also going to be the case when you're using a histogram. So my first coordinate would be 155.50, because it is always the bottom end or the lowest value 0. And then the next one would be 158.55, and because it's cumulative, they would ask for the first 3. And then the next one is going to be 161.5, and because it's cumulative data, I need to add in the 2 frequencies, and that would be 20. The other question that they could feasibly ask would be to write down what is the frequency density for the first bar. So if we can write that, work out the frequency density for the first bar of the histogram. Now, if you have a look, the class width, which we have done before, the frequency density is frequency over class width. The class width actually changes because it is 158.5 to 155.5. Okay, so then you're going to have frequency of 5, and this time it is divided by 3. So as a decimal, this is going to be 1.67. For the one on the bottom, if we were asked the same questions, the information is in that continuous mode. So if I write that as part 1 and then write that as part 2, then part 1, the answer is going to be 0, 0. And then it would be 100 because that's the top end, 18. And then it would be 200 for the top end of the next bar. And then it would be a combination of 18 and 22 because it is cumulative frequency. So that would be 40. And then for the second value, which is to write out the frequency density. So the frequency density is going to be 18, which is the frequency divided by the class width of 100, and that is equal to 0.18. And as I said, these are the types of questions that I would expect them to ask you in the reading around and making sure that you know these. On the next slide. So here we're moving on to the next element of data analysis, where we're recognizing and interpret possible outliers in data sets, statistical diagrams. This is then, we've got a formula to sort of work this out, and it could be that the data was interpreted incorrectly. For example, if someone was to measure the height of a door, to estimate the height of a door, and they put 1.8, instead of putting meters on it and they put centimeters, it would be ineffectual and we couldn't use it. So as I said, there the formulas are using with the interquartile range as IQR, and Q1 is the lower quartile and Q3 is the upper quartile. And it is select or critique data presentation techniques. So again, that would be if the scale was incorrect in a diagram, or if they'd put frequency in front of frequency density in a histogram, and I've sort of covered that before, so I'm not going to go too much into that. And also to clean, including dealing with missing data, errors and outliers. So if we have a look, in this one, I've done an example. I've tried to stay away from the WJC questions just because we've only got a small number. I think there's only like 4 or 5 past papers. So that way you can then look through them yourself and you've got the answers and you can go from there. So I've just made one up where it says that Yara is interested in an online fitness class and decides to investigate the cost in pounds of a 1-hour session from various instructors. She gathers a random sample of session costs and obtains the following summary of statistics. So she summarized this before. So the minimum cost is £15. The first quartile or the lower quartile is £20. The median is 25. The mean is 26.8. They include that in there. The third quartile is £30, and then the maximum value is 50. So using the interquartile range method, identify any outliers in the cost of the 1-hour fitness session. Show all calculations. Well, the first thing we need to do is we need to calculate the interquartile range. So the interquartile range is the upper quartile minus the lower quartile. And if we take the information from here, we've got the third quartile, which is £30, and then take it away from the first quartile, which is 20. So we have an interquartile range of £10. Now, you will be asked to sort of explain what is meant by that. So if I will be talking about it in another slide, so I'll continue on with just looking at the outliers, but it will be in a third slide now or a second slide after this. What we'll need to do then is, so to work out the lower quartile outlier or the lower value outlier, you're going to do Q1 minus 1.5 times the interquartile range. So we've got the information. The first quartile is 20, and that is taken to 1.5 times 10. So then that is going to be £5. Notice that the minimum value we have is 15, so 5 is less than that, so there is no outlier in terms of that. If then I was to do for the upper value, see if there is going to be one in there, it would be Q3 plus 1.5 the interquartile range. So then that would be 30 plus 1.5 times 10, which would give you a value of 45. Now, if you have a look, our maximum value here is 50. So then that 50 would be classed as an outlier. And how they would represent that, if I was to sort of just sketch a box and whisker plot, which will also help us for part B, which is to help us with the skewness, which we talked about. You would have, as I said, it hasn't asked me to draw it, so I'm just going to draw a sketch. And then you would have your outlier like so. So if you notice that the first quartile, sort of the minimum, there's a difference of 5, there's a difference of 5, there's a difference of 5. So I've tried to sort of do that. And then you would put 45 as your maximum, and then the 50, which is the maximum value, would be having a cross because that is classed as an outlier. I'd hope you notice as well that the tail of this is in the positive region, so describe the skewness in part B. So it is positively skewed. As the tail is going in, and then it says explain what is meant by the context of this. Now, when it has asked you for what is meant by the context, you always have to relate it back to the question. So I would say a few, what is it, fitness classes. So a few fitness classes would be sort of higher in cost, and this could be due to specialism or oversubscribed. Specialists oversubscribed. And you've related it back to the question, and also you've got that sort of positive skew. If you have then a look at the next slide, and so we can see what we're looking at in terms of what I mean by the interquartile range and what is also linked as the standard deviation. Okay, so now I'm going to talk to you about the central tendency and the variation. So the central tendency is just basically the averages, the mean, median, and mode, which you know all about. And then you've got the variation, which is the interquartile range is linked with the median, And we've sort of done a lot of work on that at GCSE level. And then the standard deviation is linked with the mean. Now, when you talk about the interquartile range and the standard deviation, you're talking about the central sort of spread of data. The reason why it's the central 50% is because then any outliers above or below are not included and not counted. And you're looking at, when you're talking about the IQR and standard deviation, you're looking at the spread of data, okay? So if it is a small value, it is concentrated. And then if a large value, then what you say, it is more spread out, varied. And those are the words that I would expect to be seeing in the context of a question. Most of the time with these, they're just specifically just asking you to calculate them. Okay, so you're told here to use, again, I've sort of got rid of the question because I'd like to sort of talk around about it and taking up the values. And generally you have sigma f of x. So that just means the frequency multiplied by x, which in this case is the midpoint because it's group data. And then sigma f of x squared, that would be the x value squared and then multiplied by the frequencies. And both of those are sort of incorporated in the formula. And they don't want you to spend a huge amount of time calculating those, and there'd be a lot of marks given for them. So they've summarized it for you, okay? So be able to calculate the standard deviation including from a summary of statistics. If they haven't summarized it, then they'll just give it out and be single values. You should know that to work out the mean, which is x bar, is equal to the sum of f of x, and that is divided by the sum of f. Okay, so again, this is midpoint times frequency divided by the total frequency. And then the sigma f, the sigma element, just means the summation of. Well, the sum of f of x has been given to you, so it would be 539.75, and that would be divided by the total frequency. And in the total frequency for this case, or sigma f, which I'll write in, is equal to 184. And that is just me adding the frequencies as we go along. So then divide that by 184, and we would have a value of, where did I put it? 2.93. And again, what they specifically want you to do, and if you read on the front of the cover, is to write the 3 significant figures unless stated otherwise. Okay, so unless you've been told otherwise to write it to more or less, you write it to 3 significant figures. That x bar meaning is the mean. So then the standard deviation is equal to the square root of sigma f of x squared, which we've been given, divided by sigma f, minus this x bar squared. There is a second formula to work out the standard deviation, which you could use, but you're going to have to calculate most of it before, because it is the summation, square root of summation of x minus x bar, all squared. So this is probably the best formula, because this one is the one that's going to be mainly given to you in terms of the summary of the statistics. And then it's just a case of plugging in the values. So we would have 7704.1875 divided by, and then we said that was 184, and that is minus, and then it is 2.93 squared. Put the square root across, and that is equal to, let me just get rid of that mark and that mark there, and then that is equal to the square root of 33.28. I just go with dot dot, and that gives me a value of 5.77. So we have the mean at 2.93, and we have the standard deviation at 5.77. You need to know as well that the variance, okay, the variance is the is equal to, sorry, the link between the variance and standard deviation is the positive square root of the variance. Now the reason why that's the case is because if we were to take away from the mean all of the different values, it would come out to be 0. And we can't do anything with it. So we square each of those, because anything negative squared is going to be positive. That gives us the sum of the deviations, and then we have to square root it because it's in a different system. One's squared and the other one is singular or linear. So this is why we square root it, and we've given a name such as variance. Okay. The other type of question you would get for this, and if I put this in purple, and if I put it in this box over here, what would happen? And they like to sort of use the mean and the standard deviation. So what would happen to the mean and standard deviation SD if the first two groups were combined? So instead of having 0 less than or equal to r to less than 0.5, sorry, r greater than 0, less than 0.5, and r greater than or equal to 0.5 but less than 1, we would just have them from 0 to 1. Okay, so what would happen to the mean? What would happen to the standard deviation? Well, the mean, because that midpoint, instead of being 0.25 for 121 of the values, is going to be 0.5 now, so that's increased. It's only sort of the 0.75 for 10 values are going to be reduced slightly, but on whole, that would be increased. Okay, so the mean is going to increase in value. And then that standard deviation is going to be shrunk because there's less outliers in that respect. Okay, there's less than that 50%, so that central 50% is going to squeeze in, so the standard deviation is going to decrease. And they like those type of questions. And again, on the flip side, what would happen if you decreased the top bars? Sort of instead of having between 5 and 10, you had between 5 and 30. So then the mean in this case would be decreased, and the standard deviation would also be decreased because everything would be squashed in. Okay. And here we're on our last section for this sort of topic part of statistics. Notice there are 5 questions and there are 5 sections. Okay, so for this applied paper, you're expected to know each of the sections well, and your time is constrained. There's a lot of reading in these, so you need to make sure that you're up and you know all of this information. Otherwise, if you think about reading a question in an applied question, it would take you like a minute, whereas in the pure section, it is less than that, probably like 30 seconds, and you already know what the topic is. For these, it's making sure that you interpret it quickly and to work your way through it. And if you're starting to get yourself bogged down on a question, I would highly recommend that you move on. Okay, because you've only got an hour and 45 and you've got that mixture of statistics and applied that needs to be done. If we have a look at this, a researcher wishes to investigate the relationship between the amount of carbohydrates and the number of calories in different fruits. He compiles a list of 90 different fruits, apricots, kiwis, raspberries, so on and so forth. Notice we have a scatter diagram, which is the part that I'm going to be mainly interested in, and we're going to be reading around. As he does not have enough time to collect the data for the 90 fruits, he decides to select a simple random sample of 14 different fruits on the list. For each fruit selected, he then uses a dieting website to find the number of calories and the number of carbohydrates. Notice these got the units there with it. In a typical adult portion of, e.g. a whole apple or a bunch of 10 grapes, half cup strawberries, etc. He enters these data into a spreadsheet for analysis. Okay, so notice there sort of 3, 4, 5, 6, 7 marks here. So you're talking about 10% of what is going to be the paper. Okay, so you need to make sure that you understand each of these elements. First part is explain how the random sample function on a calculator could be used to select a sample of 14 different fruits. That's quite a chunky sort of 3 marks for that one. So how you would go about doing this would be label fruits from 0, 1 to how many fruits are there? 90. Okay, so it's a 2-digit number. If there was up to 130, then it would be 001 up to 130. So you want to sort of get that idea of a 01 to 90. And then random number generator calculator, and then you would pick the fruits that are labeled, that have been selected. It's as simple as that. It's 3 elements. I can't see that question ever coming up again, but it might be that it's useful. You need to understand where the different types of sampling and how you can do that. I mean, again, a lot of it was stratified sampling and opportunistic and systematic sampling. Those were covered at the GCSE numeracy. So it would be an idea that you look up at those and how you would again calculate it. The bit that I'm more interested in is this scatter diagram. If you notice that it is a regression line y on x, where the coefficients are excluded. So they're not going to be needing you to calculate them, but they're expecting you to interpret them. And this is where I think a lot of students sort of fail in this element. It is where they've asked you to specifically state it and they've asked you to interpret it. If they want you to state, for again, the gradient, because let's be honest, it's a y equals mx plus c equation, and that's what the least squares regression line does. It plots the best line of best fit, which you would normally have done again at GCSE, but it plots it in terms of y equals to mx plus c, where m is the gradient and c is the intercept. So you know what those values are. So if I ask you to state them, it is just looking at what that value is for x. So down the bottom here, if I was to ask to state what is the gradient, it would be 2.9. Okay, so it's a positive gradient, which is what you'd expect given the diagram. And then the y-intercept is 12.4. And again, but I haven't interpreted them. What I've done is I've stated them. Now we need to describe, we need to interpret. So part B, scatter diagram represents the number of calories against the carbohydrates for the sample of 14 different fruits that was taken. And part A, we've sort of described how we would take those. Describe the correlation between number of calories and the carbohydrates. Well, as I said to you before, so B part 1, this is going to be strong positive correlation. And I would expect to see positive correlation, and as you can see, it's very strong. It's almost like a perfect line going through them. If they were more scattered, I would just be happy to see positive correlation. And again, if it was going in this direction, sorry, the opposite way to which the camera is going, you would have then negative correlation. Okay, so we've interpreted what that means. Part 2, interpret the correlation between number of calories and the carbohydrates in the context of this question. So it's almost as one is increasing, so is the other one. So the more carbohydrates in the fruit, the more calories you will have in the fruit. But it has to be related to the question. So more carbohydrates, fruit, more calories. And then part C, and now this is the important part. The equation regression line for the database is number of calories equals 12.4 plus 2.9 times the carbohydrate. Interpret the gradient. What does that gradient mean? What does that 2.9 value mean? Because that's basically, if I was, the fact is 2.9 is a gradient. Now I need to interpret it, okay? And there are specific words that you need to use. So that 2.9 means as 1 gram of carbohydrates increase, then you would have on average 2.9 calories. So as each gram, if I was to write that down, each gram, because it's told 1 gram of carbohydrates is increased. I'm just going to write carb. Is increased. You have on average 2.9, and again, if you have a look at what the units they're given, grams, and it is kilocalories. Increases. So as each 1 gram of carbohydrates increased, on average 2.9 kilocalories of kilocalories increases. And then explain why it is reasonable for the regression line to have a non-zero intercept. Well, if you have a look, that it has a 12.4 intercept, and it would be non-zero because there's calories in. If you were to take away all of carbohydrates, it's still got calories in there, so it could be in the fat element. Okay, so no carbs still has calories for the fruit. It still has calories in the fruit. The underlying bit, I want to know average, and I want to know the units. Okay, so if you think of changing y over changing x, as you're sort of increasing that x value by 1, you're then increasing the y value, but it needs to be related to the context of the question. Maybe a slightly better way of saying it, as you increase the carbohydrates by 1 gram, the calories will increase by 2.9 kilocalories on average, and it needs to stay on average. If you don't state the on average element, you will lose the mark. I've got one more example, but I haven't got a diagram this time. So on the next page, I'll show you in a sec. Okay, on my last sort of diagram, all I've done is I've taken out an element of the regression line. So a head teacher is investigating the relationship between the amount of sleep, which is in S hours, that each student had the night before. They took an aptitude test, just an exam, and the performance in the test. The P represents the number of marks. For the sample of 40 students, he finds the equation regression line of P on S to be. So the number of marks the students get is equal to 26.1 plus 5.60 S, where S is number of hours that each student had the night before. Okay, so what reference to this equation describe the effect? We'd reference this equation describe the effect that an extra 0.5 hours of sleep may have on average on a student's performance in the test, and describe one limitation of regression line on this model. So if we were to say that if the S is equal to 0, then P would be equal to 26.1. Okay, if S is equal to, because we want 0.5 hours sleep, 0.5, and P equals 26.1 plus 5.60 times 0.5, which gave us a value of 28.9. You were to do 28.9 minus 26.1, you would say that it is 2.8. So you would expect from this equation that for every 0.5 hours of sleep, a student's grade to improve by 2.8 marks. A student's mark, sorry. By 2 Now notice as well how they sort of on average there. They've got that sort of on average element there. So how they've interpreted it. So describe the effect of 0.5 hours of sleep may have on average. And then it says describe the limitation. So if I put that as part B, and then the limitation is the students who constantly sleep get the best marks. Well, that's improbable and impossible. Okay, so there are always limitations in these. So the best performing students are those that sleep. Best performing students are those that never wake up, basically. So it's all about the interpretation of it. Okay, and you'd expect students to have no sleep would have an average mark of 26.1, because that would be the sort of where the start of the line hits the graph, where S then is 0, having no sleep. Okay, so it is about interpreting, making sure you have the sort of units put into the graph, and also making sure that you put that word on average. I hope this has been sort of helpful, and that you can then work through this questions and see what you can do from this. Okay. Thank you very much, and I will see you in another video.